You might remember doing this as a kid, running a plastic comb through your hair and then hovering it over tiny scraps of paper to watch them jump up and stick to the plastic. Or maybe you rubbed a balloon against your head at a birthday party, pulled it away, and watched your hair reach out to follow it. Humans have noticed this specific invisible pull for thousands of years. The ancient Greeks first observed it when they rubbed animal fur against fossilized tree resin, like the translucent orange chunks of amber you see here. In fact, the ancient Greek word for this amber resin was electron. That single word eventually gave us our modern term, electricity. These simple parlor tricks are actually our most accessible window into the foundational physics governing all matter in the universe. To understand those rules, we start with a specific branch of physics known as electrostatics. Electrostatics focuses entirely on electric charges that are sitting perfectly still. Every single object you interact with, your clothes, your phone, the floor beneath you, is packed with these dormant electric charges. Before we can begin to calculate the complex power of moving electricity, we first need to master the behavior of these charges while they are at rest. Let's zoom in past the physical surface of a single strand of your hair down into the microscopic space inside. Here, we encounter an invisible property known as charge. This microscopic landscape is incredibly straightforward. There are exactly two types of players here, positive charges and negative charges. The first rule they follow is that opposite charges are inherently drawn toward one another. A positive particle will always seek out a negative one. The second rule is the reverse. Identical charges will always push each other away. A positive rejects a positive, and a negative rejects a negative. This explains why your hair fans out and stands on end. Each strand ends up with the same type of charge, so they all desperately push away from their neighbors while trying to reach the opposite charges waiting on the balloon. When you rub a balloon against your hair, it feels like you are physically creating new electrical energy out of thin air, but the universe follows the principle of conservation of charge. This means the total amount of charge in a closed space never actually increases or decreases. The friction from rubbing is just a transportation mechanism. It scrapes existing negative charges off your hair and moves them over to the balloon. The location changes, but the total amount of charge stays perfectly balanced. The universe operates a strict, unbreakable accounting system where no electrical charge is ever lost or magically spawned. This brings us to another rule, quantization. This means charge only exists in strict, unbreakable minimum amounts. The smallest possible packet of charge allowed by nature is the exact amount carried by a single electron. Think of it like physical currency. You can hand someone $1 or $2 or $1 million, but the universe refuses to split that base unit. You can never have half of an electron's charge. Because charge comes in these neat, whole packets, we can find the total charge of any object using a rule called additivity. You just count up the positive packets and subtract the negative ones. 5 positives and 3 negatives leaves you with a net charge of +2. Despite the complexity of quantum physics, calculating the foundational electrical state of matter relies on elementary school addition. Now we can put all these rules together. Imagine taking that negatively charged balloon and pressing it against a completely neutral wall. Surprisingly, it sticks. Here is the cross-section showing why. As the negative balloon approaches, identical negative charges inside the wall are pushed away. They retreat into the plaster, leaving the front surface locally positive. Because opposites attract, the negative balloon securely locks on to that newly positive surface. This observable physical bond is the predictable result of quantized charges following the laws of conservation and attraction. There is one final, mind-bending property of electric charge to understand, and it is known as invariance. Invariance means that the exact measured charge of an object will never change, no matter how fast that object is moving through space. We know that when physical objects travel at extreme velocities, properties like their mass can increase, and their experience of time can slow down. Yet, through all of that, their electrical charge is absolute. These same unchanging mathematical rules govern everything from the static shock of a plastic comb to the fundamental behavior